Because we know that in a high layer, just our computer or just the human language.
ও বলে
And
কারেন্টই
the
হলো
middle
বাসটি
layer
যায়
maybe
হলো
is logic expression, and the lower layer is the programming language or computer language. And for the hardware, maybe it's just the circuit or just the electronic circuit. This is we are just here we only to talk about the middle layer, logical layer. And the logical layer just to describe our human expression or human question and translate our human expression into the logic expression. And then the low layer means just the translate or just to coding our logic expression into the concrete code. We have also during our course, we have the 4 experiments just to let you to do practice to translate our logic expression or our just the coarse concrete algorithm into the concrete the coding or concrete the programming codes. This is just to translate the middle layer to the low layer of a programming language layer. And based on programming language, you can run and you can to implement or to check whether or not its output is what as our expected. So it is just from this different layer. So the propositioner, it is just to make the computer understand what the variable can be referred to or can be described as our
পরে
human,
দেখবেন
human
দরজা লাগাই
sentence.
দিতেও
Here, just to say only just this declared the sentence that also with the true or false value, then we can translate into the proposition. So that is from the middle layer means that if you just make the logical variable or proposition is we are just using the concept proposition, and in the low layer this proposition in the future will be described as a programming variable. So programming variable in the future, you are just writing your code. You should be understand in our human word or in our human language. This is just referred to true or false the sentence. It means that the declarative of the sentence that is either true or false, but not both. If it's just both, that means it is not determined. Computer cannot to cope with non-determined things. You should make computer to understand 0 or 1, cannot both. That means you just only to store your variable 0 or 1. You cannot store the both variable in the both value in one variable. So it is not both. That is why we cannot say both. Not both. We cannot both for your just that. So if just to not determined, not sure in the future or in the just the human height or human level, then cannot be described as a proposition or cannot be translated into the programming variable. You should to make it clear because in the future you want to assign or just some the concrete value to this variable. If you're not sure, then you cannot make understand what is the output in the future. It is indeterminate or it is cannot control by a human. It is just to the sequence or randomly to give out output. It is not so. The propositional should be just it is a declarative sentence. So for this, what time is it? It is just the question sentence. We cannot translate or cannot call it the proposition. And so it is just the proposition or variable. So for the node layer, we know that when you just want to writing code, you are just as you are do your practice in the for experiment. Maybe you are writing the concrete code. First, you should to define many the variable, and this many the variable is referred to the proposition for the low middle layer, and for the high layer for our human language it is the declarative the sentence. Okay, it's just refer the bool, for example, the bool type variable. Okay, and then after you define many the variables, then you should to writing down about the expression. So expression, it is just using the many the operation to combine your many of the variables you have defined. So we should have the logical operators. These logical operators just want to combine the many logical variable or propositional, and then to describe our just the expected the hope or goal. Okay. So logical operators just to compound, just combine the many the simple sentence. Because in the middle layer we just call the logical operator, and for the high layer maybe it is conjunctive the words. For example, is not and or if and only if, such as these words. These words just in the high layer, it is just the connected words, just to connect many the simple sentence to the compound the sentence. Because we know that if you want to describe your questions or your task, you can using the many the compound sentence. And if you just divide the many the compound sentence, you can just divide this the compound sentence into the many the simple sentence and the connected words. So for the middle layer, we are just to translate this simple sentence into propositional. And for the connected words, for example, and, or, such as these words, we are connected to or translated to the logical operator. Then we can just for in the future we can to easy to translate our just the human sentence or human question into the logical expression. Means propositional and logic operator. Then we can just describe the logic expression. And we have 5 the basic the logic operator. It is just the negation, conjunction, disjunction, and conditions or bicondition. Just for the symbol, we are just using this logical not, this is logical and, this is logical or, and this is a condition, and this is a bicondition. Maybe in some the different context, maybe that you have the different the symbol, but they are also means by condition. Maybe sometimes just use this. It is just depend on different the context about your textbook. But the meaning, the same meaning, it is by condition. Okay. And for this inclusive or, maybe we going to mention more, but this 5 is very the basic. Okay, the 5 the basic the logical operators. Okay, and we also to using the truth table to define or to show about the table about this the truth value. If we just because we know that for the logical proposition, we just from the definition we know that it is true or false for each the declarative the sentence with the concrete the true or false value. So for each the variable, and this variable maybe logic variable is referred to propositional the name. It is just to have a true or false. So the the negation or just the not, logical not, just use this symbol, and then we can to define clearly about this the truth table. So truth table can be seen as the rules. The computer just followed or obey these computation rules to give out our logical expression computation result. Means if you make the computer to do inference or to do the computation, how to follow there are many the logical rules. So just based on the truth table. So we have studied the truth table one by one for each of the logical operators. And also we have just the experiment one, just to let you to write down your concrete the programming code to implement this logic expression for the truth table. So it is means we just to do your practice how to translate the human language into the logic expression, and then how to translate the middle layer logic expression to the low layer, the computer language or computer codes, just to do your practice in the experiment one. So the truth table is very basic, is a very the basis, or just can be seen as the rules followed by the computer computation. So we just give this basic five. This the five they have mentioned the basic the five operators, and the inclusive or just use this symbol we tend to mention. If you like, you can just to see by yourself, but we are just mentioned you should to understand, and yeah, just expected you should to decide or remember of this basic the truth table for the five basic operator: not, and, logic and, logic or, condition, by condition. So this is the five, the table 1, 2, 3, 5, 6. This is basically the five the truth table should understand well. And maybe we just if you just to understand from this output or this rules table, and we will find not easy to understand. It's just the true, not P is false. Okay. And for the logic AND, that means you will find this result. And this is just because we know that for each the logic variable P or Q, and each of the P or Q, they have the two cases. So from the counting rule we have mentioned in the just the chapter, the counting we have just to know about. So today we are just the overview session. So maybe we are going to compound the many the knowledge during our course to understand about some the rules or some the knowledges of things. So just from the counting rules, we know that for each of the P or Q, they have the two cases. So all together, P or Q or P and Q. Because here just the AND, so we should to using the logic or just the counting rule, using the AND rule. So AND rule using the just the product rule. That means here is the two cases, and these also two cases. So using the multiple, using the time, 2 times 2. So altogether is four cases, 1, 2, 3, 4. So 4 cases for all the possibility. This is all possibility for the value. This is just the all possibility P or Q. That means when P just to true and Q may be just true or false. When P is false, maybe also the Q is true or false. So we have the 4 or the probability. So from the counting rule. And the truth table for the logic AND is output for all the probability. We will find only one cases to get the true, and the rest of the 3 is false. So from this logic AND, we can understand it is strong. It is strong. That means if you just want to the output, the result is true, then you should both P or Q get to the true value. Otherwise it's false. So it is strong. So just we have from the understand, because the middle layer, the logic AND is referred to high layer is the AND. And just from our human words, the meaning AND means together. You should both satisfy these two something, A and B. So that means A and B should be together. So it is strong. A or B for this logic or A or B is not strong. One of them is okay. Both is also welcome. So it is for the logical or we will find we have many the truths. Only one case is false. False that means just the both get the false, then we get the false. Otherwise, if we have either one of the T or truth, then finally is the truth. For the condition should be careful. This is we also have three truths, only one false for the final result. Why we just get to the have the three truths? Because we have just like this. If our because this is a condition, if just from the concrete the program language we have the keywords, that means if, then just can be seen. If we write down or translate this logic expression into the low level programming code, that means if P then Q. If P then Q, just write down your concrete code. Okay. So if the statement, and for all the truth table for the condition, that means it is the weakened the condition. That means if because we know that if your condition this P is wrong, false is wrong, because then no matter the Q is true or false, finally is true. So I just based on your wrong condition to get anything, you cannot to say I'm wrong. You should to make sure I'm true, I'm right, because your condition is wrong. So maybe everything is possible. Just based on this idea, if your P is condition is false, then no matter the Q's result, the final result is true. So it is that is why we have the three truths, only one false. And for the by condition maybe is strong because it is just referred to our human words, the connected word, if and only. If and only. So here we have just the half with half. That means we have the two true and the two with two false. So it is that means only they have the same value. Both get the true or both get the false, then we can get the finally by condition the value is true, otherwise is false. So it is just from this truth table, and based on this truth table, computer can just to compute the other truth table for the logic expression. For example, we can compound many just this expression or using the logical variable or propositional and logical operator. We can just to describe the logic expression. For each the expression, we can just write down. It is the truth table based on the many the basic the logic operator. We can write down like this. Okay. So here just to give the way, if just to look at or just remember well about this truth table for the 5 basic logic operator, then we can easily to write down the truth table of the logic expression. Because for each one, we can, for example, this is the last, this is the noun about the expression, but we can say here can be the whole, and also here can be as a whole. Here can be the whole, and here can be the whole. And then from this column the value, we can just based on this condition. follow this condition. So here, P and Q, not only the logic variable, maybe is the expression. P or Q may be referred to logic expression, just as this. Here it can be seen, all can be seen as a P, and here all can be seen as a Q. Okay, but here P is maybe is a logic expression. Also, the Q also is a logic expression. Based on these logic expressions value, and then we can just using this finally the truth table for the logic expression for the basic the logic expression truth table. Okay. And here we just should to make remind about the condition statement we have mentioned it, because this is a very important for just the logic expression. It is not different for the logic AND or logic OR. It is very simple, but for this condition statement is very strong because it is just to very important in the future, especially for our programming code. That means for each language, just the language, the syntax, they have many some the statement, especially the condition statement is very popular because it just give us the way to describe some the condition. Based on this condition, we can do any other things. So they have many the ways can be translated into this condition logic operator or condition statement P, condition Q. They have from our human words maybe if P then Q, P implies Q, and sometimes P only if Q, P is sufficient Q and sufficient condition, and when we have the word when and necessary follows from. So we have many these things or many these just the words, but it is have the same meaning for the condition. So the condition statement, it is just for the condition, the logic operator. Okay, and we have just about this example. This is example just to translate how to translate our the real world sentence or our the human question into the logical expression. So it is just to translate our the high layer into the middle layer. High layer it is our the human language. Okay, and the middle layer is the logic. It is the logical expression. Logical expression. So we just have mentioned that just to translate our the question, we can to see as our question as a compound sentence. So first we divide our compound sentence into the simple sentence. So here is the simple sentence, and here is also the simple sentence. Okay, so we have the three simple sentences. For each of the simple sentence, we just give them preposition or call it logical variable, and then to select out connect words. Here is connect words only if and or, and then translate this connect word into the logical operator. So it is a very simple or directly we can translate only if condition or is logical or. So finally we can just give this translate transition result. It is just to give the logic expression. So only if just the condition, and for all just like logical or. And here just using the not, sometimes we can to abstract not. So here are, it is you are freshman. And sometimes if you just for simple, you are not freshman. So also can as a whole, it is just depend on you. If you just want to make the focus on about your not, so you can abstract this connect word not, and then just add this translation about the final logical expression. And we also just to give some the logical equivalence. It means we have the many the logical expression, how to determine whether or not these two logical expression is equal or logical equivalent. So here just to give the logical equivalence. So logical equivalent for the computer side or computer world, it is just means they have the same truth table. If they have the same truth table, for example, it is T. We have 1, 2, 3, 4, 5, and followed with 3F, 5T, 3F, 1, 2, 3, 4, 5, 5T, followed as with 3F. And the same, this is just all the possibility, the input. Because over here, we just have the 3 variable P, Q, R. For each variable, we have the 2 cases. So based on the counting rule, especially for the sum rule, productive rule, we have 2 times 2 times 2 is 8. So we have the 8, the all possibility. For all these possibility, if we get the same, should be careful, all should be same. Then we can say it is a logical equivalence. Logical equivalence. Because from this truth table, they are same. So we can say this two logical expression, although they have different style, but finally the value is the same. So it is logical equivalence. So here we just using the word logical equivalence because the expression is not equivalent. They are different the style, but their logical value, the final value are same. So we can say logical equivalence. Okay. And based on this logical equivalence from the truth table, we can just implement the equivalence the rules. And we have just give each the basic or formulas some the equivalence the name. For example, here just have the domination laws. That means it is have to have a logical variable to computation, but finally it is not to dominate the final result. So it is can be said the domination rule. It means although the P just to do some the computation, but finally it cannot to affected the final result. It means it is not related to as the P's value. So it is dominated by the concrete or constant value, P or false. It means P or true. So no matter P's value, finally is true. So it is domination laws. Okay. And some, for example, is a double negation law. That means not, it is just the sure. Not P is not equivalent to P itself. Okay. And I also have the Morgan law, and we also to give the Morgan law the extension the rule or general rules that means not is not symbol is very strong. We just want to push this symbol, logic symbol, not symbol to backward. Then, if just to meet everything, want to change. So the first to meet P and change to not P, and then to meet this operator and change to O. And then finally he meets the Q, change to not Q. So just obey these rules, we can easily or directly to write down the Morgan law, the result. Okay, and this is for the absorption law. It is similar as for the domination law, but it is, for example, here the Q. It is just from the left side we have the two variable to computation P or Q, but finally only result to P, then to care about the Q. So So we can say Q is absorbed by this expression of final result. So it is absorption loss. Okay. So it is have a basic equivalence from is already to proved by the truth table. So finally, we can use these basic equivalence rules directly in the future for our equation for our human. That means sometimes we have the many others these logic equivalence rules. Then we have just to this just to make you understand or remember for these rules. That means condition P condition Q can be described as not P of Q. That means we can using the other equation is logic or and logic is the two symbol to describe this condition symbol. So this is just to give out the way. That means if just to for the low layer programming language, it is a computer language, and we have know that program language also have the higher program language or lower or machine code lower language, or sometimes have a middle language. Middle language, for example, have many the intermediate representation or intermediate language. Higher language such as the C or C++, that means you can just they have many the words or keywords similar as our human word. For example, the condition, they just use if, then else. If then else is a keyword. It is can be seen higher. And for the middle layer, maybe just have the many, just have the middle, the stack or mini, have the stack, have many the middle the layer, but it is not readable for human. And the machine layer or low layer, machine layer, that means just such as the move or jump something. It is very the low layers programming code. Okay. So it is just for this, it just can be translated efficiently for the compiler. For example, C or C++ compiler. Now compiler just translate your this condition statement into this basic statement. For example, the logical or. And then can be using implemented by hardware. Or we know that our programming code can be seen as a software. And software finally should be translated, should be compiled into the binary code. And then this binary code is running in the hardware. So how to translate these many the logic operator equation for the condition. So we just translate to this as using the logical or, and similarly have any other things. That means the by condition. You know that by condition can be described as the two conditions, P condition Q and Q condition P. And we also know that P condition can be written like this. So finally we can say it like this. P condition Q also can be using logic AND or logic OR to describe here together. So it is just using the equivalence rules to translate out the existing logic expression. Okay, and here just to give the way how to contact the new logical equivalence based on this existing logical equivalence rules. That means we can just this is for our human. Because based on these many the rules, we can to influence many the new equivalence rules. And these rules also you can input for computer, and computer can be based on these rules to do influence magically. And here is have many examples to for the predicate the logic. But we have mentioned this many is propositional logic. This is logic just have a propositional, then it is a logic operator. And for the this predicate logic, we just introduce the two quantify the word or quantify the symbol for all and for some. Or for some, is the two special symbol, and based on these two special symbol, we just to make the condition or make the just the restriction for the logical expression, and then we just call it the predicate logic. Predicate logic, okay. And this predicate logic just it's similar as our the prepositional logic, but we are just have choose the special symbol for all and for some. And based on for all and for some, we also have the many some the rules. So here we didn't to overview more. If you like, you can just to recall the previous slide or previous PPT. You can just to recover about many things. And for the predicate logic, we also to introduce how to do the translate, is how to translate some the sentence. So the predicate logic you will find we want to research or study about the simple sentence. And for the prepositional logic, it is only to consider just the sentence for whole as the variable. Now, predicate logic, we just divide each of the sentence into the two main parts. The first is the subject, and then is the predicate. Subject and predicate. So it is just have a more or deeply. So for this sentence, maybe it can be seen only the one a simple sentence. A simple sentence. So this is a simple sentence. If you just using the prepositional logic, you only describe it as a one variable. But you sometimes want to study deeply for this simple sentence. It means the sum of the two positive integers is always positive. So we just extract the meaning, the things from this simple sentence. That means this here we just care about the positive. How to say positive? Okay, we just using like this. There's a positive and two positive. So we can just using and here just if x y, and also we just using the qualifier for all x or y. If x larger than 0 and y larger than 0, it is just to meet this two positive integer. And then we just using the condition. Then the sum, what means the sum we just x plus y also positive. So here is a positive, we just say using this symbol. So although this here is a simple sentence, but for the predicate logic, we can just to divide this simple sentence into the subject part and predicate part. Predicate part just to describe some of the features. For example, here is just the positive or just the using this whether or not using this condition. Just from this condition to infer this result, the sum also is positive. Okay. Similarly, here is also if just from the sentence, the structure from our human, it is just a simple sentence. But our just the predicate refers to just the qualified word every we just translate for all, and real number except 0. Real number except 0 has a multiple inverse. That means here except 0, so we just say if x not equal 0, then, and here just has, and here has means there is a sum. So here we just using some the another qualifier symbol. So the predicate, this is the predicate just give out the way to study more deeply for simple sentence. Okay. Okay. Now 5 minutes break. Okay, we continue to overview of the course, and this we just session. This session we just to overview about the logic, because logic is a very basic important. So we are just to overview the more about this the knowledge, because we know that the computer just based on the logic theory to work for us. So here we have the the type for the logic. The first is the general logic, the propositional logic, and then the second is the predicate logic. Predicate logic is just can be seen as the extent for the propositional logic, because we know that propositional logic only to translate or only to consign the simple sentence as a whole to describe or define as a proposition. And then it is maybe in the future can be translated the simple the programming variable. But the predicate logic just to divide out the simple sentence into the two basic parts. The first is the subject, then is predicate, and also we are extract some the quantifying the values or variables such as every for all, just using the for all, and for some, and there is, it is just to translate it is for some the symbol or the logic symbol is the qualifying the words. And similarly for just have based on this logic, then computer can do their inference. So in the computer, they have do many the computation, but this computation, it is in fact, it is just to do the inference. So computer only can do the raw inference. That means you should to obey or you should to design the many the inference rules for the computer. Then computer can do their computation. Computation in computer is means inference. So it is not the different meaning for our human, because for our human maybe the computation is just to do many some of the complexities the computing. For example, the 3 times 5 it is 8. How to do for computer? It is just to translate this into the basic logic. They should to the all of them should to logic. That means the first we translate 3 into the binary code, and then this binary code to define this logic and then to give you out the final result. Not as our using our human rule code. 3 times 5 was 3 5 is 15. 3 5 is 15. We just directly to give the 3 5 15, but computer did not do as our human. We first translate the 3 into the binary description, and then 5 also the binary coding, and then to using the logic and to do this logic, this multiple, and then to use this binary expression into the final result, 15. So the difference. So they have the many the rules for the inference, and we have just like this. This is just using the symbol, and here is the symbol like this. It is just the imply, and this imply just using the just sometimes imply can be seen using some the just using imply like this symbol, and this symbol can be defined as, for example, P imply Q. P imply Q. It defined means that P condition Q is always true. P condition Q is always true. So it is a tautology. Tautology means that it's always true. So this is described as writing down for our human like this. P, if P, so P or Q. So it's just using this bar, and over the bar can be the condition, and under the bar can be seen as this is just can be seen as a result, or can be seen as it is the inference result. So it is a tautology means that, so what's the computer to do all this inference? For our human, maybe we can understand, or just based on this condition, then we can do some inference result. But the computer, how to do that? It is easy, just to translate this into the condition expression. That means for the over bar, we just do the condition P, and the bar can be the result. And so using the condition symbol. So if P then Q, whether or not is always true. If it is always true, then we can say P in R and Q. So we just do the inference. So computer to do inference just to translate into the condition. So that is why it is optional for the condition statement. If statement, we can say the concrete code if statement is very popular because it can be do some many the inference things. And here is an example that means we can translate our inference patching. We have this condition 1, condition 2, and it gives the conclusion. We make to sure whether or not we can do this conclusion. And then we first to translate into the logic expression, and based on the logic expression to manage the rules or inference to check whether or not it's a result. So computer to do inference just to translate into the logic expression to do the inference, and followed by the meaning about these things, or many about these inference rules. Okay. Also have many similar examples. Okay. So for the chapter 1, we just the logic, and it's the inference. Logic just to describe how just the feature, or just the human creation, or just the algorithm, just how to design. And the inference just to do the computation, how to do computation, because maybe you can design how to combine, how to do your computation. And in the future, we also to as the algorithm, because the algorithm just to have the many, follow the many of these rules, or many of these computation rules. But this computation will just to let you to design how to do their computation for computer, combined with variable and operators. Okay. And for the chapter 2, just mean that we can extend, because when the chapter 1 just only the logic. That means we understand well about the raw value. But we can know that the computer not only to cope with the raw variable, raw value, but also can do the many things for our human. How to do that? And then the chapter 2 just the set function. And in fact, these two is or sometimes the matrix. And the first, the set and function is very basic for the computer coding or programming language. So if we just to understand the set and function, then we can to write well about the programming code or programming language code. Okay. And how to describe the set for the computer, because now from the chapter 1, computer to understand well about logic, because we have a logical variable and logic operator, and computer understand well. Okay, that's from the truth table. Now, how to make computer understand set and set operator. In fact, computer set just understand set using the predicate logic. And here, just the first infinite set and power set, it is a basic idea for the human. And here, just should be careful to have much attention for these two basic concepts. The first is power set. This power set should be careful. It is just to give all the possible the subset. Subset because we know that it is abstract some element. Because here we have a set with the 3 elements 0, 1, 2. So how to choose about power set or subset? So subset for the computer, how to understand? This is just to give the understand to try to give the power set for the computer to understand. Because for our human, we are easy to understand. Our power set is each the power set element is the subset for the set. For example, itself 0, 1, 2. They have 3 elements. You will find for each of the set, for example, here, the element in the power set, it is a subset of the 0, 1, 2. Okay. So how to understand for computer to understand the power set? We cannot to make the computer to understand in our human ways, because our human ways means that it's a subset. What means subset? Subset, it is just come from, the element come from this. So we can change our idea. That means we know that for each of the element, we just give their position 1, 2, 3. Okay, we have 3 elements 1, 2, 3. And for each element, you want to choose some element from the existing element as a subset. We can to change our computer understand the truth or false these days. That means for each of the element, we have the 2 cases: choose or don't choose. Choose means true, whether or not you choose this element. For the I position element, whether or not you choose. If you choose, it is true. Otherwise, it's false. So for the subset, we just to translate as the predicate logic expression. That means whether or not you are choose this position I element. If I choose, so the I element is 1, is 2. Otherwise, if you don't choose, it's 0. So we are just like this. And here should be careful for some the empty set. This is a very special. Empty set just like this. We just use the symbol this for the empty set. But for this, should be careful. This set is not empty because they have 1 element. Although this element is empty set, but this is finally this set is not empty because they have 1. So for this the 1 element, this is the set of the power set. They have the 2 element. That means you are choose this element because this element is a special set, empty set. Okay, you are choose or don't choose. So we have the 2 cases. If I choose, it is self itself. If I don't choose, don't choose. You have only 1 element you don't choose, so empty. So empty, this empty, just use this symbol is means just like this, empty. So here you will write down like this. We have the 2 cases empty. We don't choose anything, and we are choose A. I choose this A. Okay. So the power set, if you just using this is A, you write down like this A, then this power set you can write down easy to understand like this. But here we just this A is a special set, empty set. So that is why we have like this. So this is just for the special set. Okay. And we just also the Cartesian product. This is just to make sure about to describe our just the time, the set time. because we know that we can just use the predicate to describe our set. Because we can set A can be described out using this the predicate. Here is, for example, is A's element, and here A should be satisfying some the predicate PA. It is our just described. We are just using equation for this. This is the predicate A. That means A should satisfy some the special predicate logic, for example. So just based on this idea, we can just define some the set production or this computation. For example, the A times B. A times B we can just describe as like this. This is the element, this is the triple element A, B, and here is the predicate A and B. And this predicate just using the predicate, the logic expression. And that means A belongs to the set A, and so this is logic operation. So we have the logic and B belong to logic set B. So here just can be seen as their logic expression. So we are just using logic expression to describe our set operation. Set operation. Here just the product. And similarly, we have the set the operation have the union, the section, complement, and some the subtraction have many. We are just defined it is a logical operator to describe our set operator. So that is why we can extend our predicate logic into the set, and based on set, we can describe well or just frequently for our programming language codes to solve out the real question. Okay. And here just to describe for some of these just the production or just the set operation. And this Descartes, this time, or we can say the set, the production can to define the relation. That means for the computer, they can understand the relation is different for our human idea. Our human relation, maybe you are just to consign their social relation, for example, just the classmate. What I mean, classmate relation, maybe human, just the idea, maybe social idea you can say, or your classmate, maybe have just have a study in the same classroom, in the same just the university or same the major, your classmate, okay, just the best of it. But in computer, they don't care about this more social idea. They just say, if just the relation you have classmate relation, you should give me about the table. And in this table, you should to combine together. So you will find in the computer, they are just have their relation. It is the same as just as the truth table. You should give the truth table, computer only to obey the truth table. Similarly, if you just give relation, you should give us this relation set the database or relation set this table. Based on this table, if they check or search, oh, you are just existing in the table, then we can say you are classroom. Otherwise, we don't understand what it means classroom. So in computer, their relation, it is a subset of the set. So computer, they are just describe our relation as a special, just the Cartesian the production the set, the special set. And that is why in the future we just to describe our the function as a special relation. So also can be seen as a set. So you will find just the maybe the last chapter graph will also to describe about the relation, also to describe of the set. Sometimes the set to describe the table. The table maybe we just use the matrix to describe the table. So you will find they have the same relationship. In computer science or computer world, they are just understand of the set as a predicate logical expression. And we can just many ways to describe of the relation set. The relation seen as a special set, and we just can be described of the relation have using the table and the graph, have many other things. Okay, and for function as a special set. Okay. So the set, the summed operation, and here just show you about the simple or just choose one the disjoint set. Disjoint set, that means we are just to can be seen as a unit. Sometimes we can just unit the set. Okay, so unit the set, we are just to for each the value, either or. So just using these next things. Okay. So we are using the logical operator to describe the set operator. That is the set union, set intersection, and here. And also we have just based on the logical equivalence to refer to the set identity. And this set identity can be seen as the set equivalence. The set equivalence rule. Based on this many the set equivalence rule, we can do the many the set operation or set computation. So it is very familiar with the logical equivalence rules. We have mentioned the domination law, and here maybe it's similar as logic true, because if you just say your U can be described as here is A and here is PA. Yeah, just the predicate is always true. It's always true. It's always true. So if also true, then we can say it's a set unit. Okay. For the U, if some the set A unit with this total set U, then of course is total set U itself. So it's dominant. And similarly we have mentioned absorption law. Absorption law, it is just here we are just the B, set B to do the computation, but finally only to get the A result. We don't to care about the B's value. So it is A union with A intersection with B. That means A union with A B's common part. A B's common part, of course, is a subpart of the A. So finally, A union with a subpart, a subset. It is a subpart. Of course, finally is A. Then to care about the B's value. Then to care about the B's value. So it is absorption. So it is easy to understand for our human because we have learned in the middle school to understand what it means for using this the set the features. But now, how to make computer to understand these rules? Just based on logical rules because we have already to make the computer to understand the logical equivalence rules, absorption laws. We have mentioned in the logic, and now the computer also can understand this well. For example, we just to show you about, we have mentioned these rules. Maybe just this here. We have also to show this about the absorption law. You will find very similarly, and this the dominant law. So you will find it very, very similar. And here just it is very, very similar. Okay. So that is why we just make some convenient map from the set and predicate logic or logic. That means set is very familiar with the logic. That means in the computer side, we are all of the set and state operation translated into logic and logic operation. We just do this translation. Then we can use the computer to describe about the many the set and set operation on the human world. Okay. So set can be seen as the translate or extension about the logical rules. Also, we can do some proof for the set. Here, just prove the set. So you will find finally we translate this. You will find this is the logic. So here translate into the logic. We are do the proof about this set features, but finally we just translate into this logical expression or logical rules. So you will find they have many the closeness of relationship between the set and logic. The similarly set and logic, and also we have already to have existing this set rules we can for our human. We can use these set rules to do some proof or inference step by step by the existing. It's easy to understand. Here just the example. This example just give about the shoe. Using the existing set nodes to do some inference. Okay. But for computer, maybe they are easy to understand to for this truth table or just have the logical expression rules. And based on logical expression rule to inference or to refer to the set rules. Is okay. And then we computer now understand well about the set because all the set and set operation can be translated into logical and logical operation. And now we can to define the function. What do we know that if your programming code can be when you first to learn your programming language, if you can write down your function or write down your procedures, then you can to do or design your programming or software by yourself. So function is very important. So for the computer, how to understand function? Function in computer, it is as a special set or special relation set. So function can be seen as a special, it is a special relation, and it is just can be using the map. It is from the input to output. Sometimes we can say input the raw can be seen the domain, and output can be the code domain. It is sometimes for the element in each element we can say it is a pre-image and output the output result can be seen as an integer. So it is just from the function. Function just can be seen as from A to B. This A to B have a relationship, and this can write down map from A to B, map from A to B, and this is a concept for the function, but it is easy to understand about things. And since function is same as a relation set, so we have the three ways to describe our function. The first is the relation set. The function, you can just describe the set as a function. And the second way, you can just use like this, the map. And this map by party graph, we have just from the the chapter graph, it is means by party. Is the by party have the two parts, input part and output part graph. Okay, by party graph, so it is, can be seen the graph, and the later we also can say this. The third way to describe the function is a table. Just using the sometimes maybe you can use the matrix to describe your function. So that is why how many your computation can be translated into the matrix. Okay. And also for the function, we have this the special function. The first is one-to-one. Second is on-to. The third is both. Both can be seen one-to-one correspondence. Okay. So one-to-one means that it is for each value you should to have just to you have the map only one. So here you have the two C or D input to map the same Z. So it is not one-to-one. One-to-one. If you just have, for example, here is one-to-one. If you have the output, you only one arrow to connect to, and similarly is only one, so it's one-to-one. But here is not. And onto, what means onto? Just for these words meaning, onto on. So for each of the value, you should sum the arrow onto. So here is onto. We don't care about how many, but you should have. But here, for x value, no arrow onto it. So it is not onto. So it is not onto. And here, for each of the value, output we have arrow onto. So onto, just from the output value, each the output value we have arrow onto. So it is onto. And if both satisfy one-to-one and onto, we just call one-to-one correspondence. So one-to-one, it just from these words means one-to-one. You cannot to say this is two to one. So it is not one-to-one. And here is one-to-one. Here is one. If I have arrow, only one. Otherwise it's not one-to-one. So this is just to have the special for the function. And also we have the special features for the function increasing and decreasing. So increasing, of course, we are using the logical expression to define what means increasing, just like this. If we write down this word or this logical expression, then computer can understand what it means increasing. And for our human, maybe just from this picture, we can say if just run, go forward, and also from the X, you are just the nudger, and then your Y also nudger, it is increasing. But here, when X nudger, you will find Y is down. Y is down, so it is decreasing. So decreasing means that as the time go forward, your final value, whether or not is higher or lower. If higher, it's increasing, so it is similar as our word meaning for our human. Increasing, we can understand is go up, go out, grow up, and decreasing is down. is download. So download is just, so for computer, he can understand like this. If for all x, all y should be careful for all x or y. If x is smaller than y, then they'll imagine fx larger than fy. It is decreasing. So it is not the same. X smaller than y, but fx is larger than fy. So it is decreasing. And increasing means that x is smaller than y. The imagine also smaller than y's image. That means x is smaller than y. Their output also smaller than y. Input value smaller, then output value also smaller, then it's increasing. It's the same. So computer understand this definition, but for our human, we can just understand for our just the human world. When x growing, y also growing. So it is like this. Okay, here just have about this example. We also give you homework, also to discussing about this homework. It's just from determine their 5 basic features for the function. And 1, and 2, or both, strictly increasing or decreasing. Just based on this, understand the features. Sometimes you can do, for example, this. If you just draw the picture, it will be easy to understand. The first is 1-to-1. 1-to-1, that means if you just for this the 9, if how many in the hit, and here just the hit, here just the hit 1. So for this each the y, we only hit the x. So this is a 1-to-1. For example, if you just like this picture, this is the picture. For example, is y equal to x squared. X squared the picture. Okay, the x squared picture, if you just have this, you will hit the 2 value. For the same y, you are hit 2x, so it is not 1-to-1. So if just for this only to hit 1, then it is 1-to-1. Onto, what means onto? That means for each the value, all the value, all the y you should to hit. Now we don't care about how many hit, but you should must hit, then is onto. So for this, it is all the value you can hit, so it is onto. Okay. So it is both. It means 1-to-1 and onto. And now for the increasing or decreasing. So when x larger, you will find here y also larger. So it is increasing. And similar here is when x grew out and y also grew out. So it is increasing. So increasing like this. Okay. So today we just only to overview of the chapter 1 and chapter 2, because this is a very, very basic for computer. This is just the logic and set. Because all the computer understand our human concept, it is based on the logic. So the logic can be seen the basic theory for computer. And if a computer understand logic, then can be described or learn some the set, which will also learn the function. Based on the function, they can to write more or design many the things, which means upgrade. Next, the session will overview about these things. And this session or today, we only to overview the very basic topic. First is logic, second is the set and functions. Okay, now discussing time. So any question you can discuss in here. You can describe your question in the live chat room or in talk room.